Hello and welcome back to EGR 151 Electrical Machinery. In this unit, we're going to be talking about magnetism. This goes along with Unit 4 in your textbook, which, as always, I recommend you read either before or as you go along in this presentation. So what we want to discuss in this particular unit is a number of things associated with magnets. We're going to first look at permanent magnets, specifically their properties. We are going to talk about magnetic poles of the Earth. There's, of course, a difference between what's referred to as the axis poles and the actual magnetic poles. So we're going to discuss the difference there. And we want to discuss how different electromagnets work and how they operate. In addition, you should be able to discover the polarity of a magnet when you're dealing with an electromagnet. The fact is the way it's assembled and the way the current flows will tell you what the polarity is, so you need to know how to do that. In addition, you should know the different systems used in terms of measuring magnetism. There's a number of different quantities, properties, units. These all are important for you to be familiar with. And then, of course, any additional terms used to describe these. So these are these various quantities and properties associated with magnetism. If we look at permanent magnets, these are essentially magnets that you don't have to put any energy in or any power in to maintain their field. You're probably familiar with them, things like refrigerator magnets, any type of magnets used to hold things together are usually permanent magnets, etc. And the key thing about these, of course, is they're not in any way charged, right? They don't have a battery, they're not plugged in, so they have a permanent magnetic field. So how is this accomplished? Well, if you look at a random piece of material, you will see that atoms are essentially disorganized, right? They're aligned in all different ways. And of course, this is a 2D representation. The fact is, in a 3D representation, they're essentially going to be all over in all different directions in three different directions as well. So if you take a look, all material, or at least all material that can be magnetized, has a north and a south pole to it. Just about every atom or molecule has some level of polarity, but they're not all permanent magnets, and the reason why is because they're essentially all disorganized, and as a result, the various magnetic fields generated by these atoms or molecules don't align, they cancel each other out. On the other hand, if you align these, right, if you use a method for aligning these so that all of the north poles are pointing one direction, north or positive poles are pointing in one direction, all the south and negative poles are pointing in the other direction, you will generate a series of magnetic fields from each of these atoms or molecules, and they will reinforce each other, and as a result, they'll generate a magnetic field outside of the material. When we tend to think of magnets and materials, we tend to think of iron. Iron is a material that is relatively easily magnetized and it's used for a lot of different magnetic applications. But it turns out that many different metals or materials in general can be magnetized. And there's three different categories that we put materials into. If a material is easily magnetized, meaning we can get those atoms to line up easily, this is described as ferromagnetic. Right? Ferro actually comes from iron, ferrous metals, and the different materials that are ferromagnetic are iron, nickel, cobalt, and manganese. Right? These will make relatively good permanent magnets, at least temporarily, and can also be used in electromagnetics. Although iron is very inexpensive, so we tend to see iron used more often than the other materials. if we have materials that are able to be magnetized, but it takes a great deal more effort, they're referred to as paramagnetic. And things like platinum, titanium, and chromium are all examples of things being paramagnetic. And for example, chromium is why stainless steels, for example, are not magnetic, because they have a lot of chromium in them. So that kind of eliminates their magnetizing ability. Lastly, things like copper, brass, and antimony cannot be magnetized. The fact is, the magnetic field will not permanently change this, and these are referred to as diamagnetic, meaning they cannot be magnetized. Magnetism is represented as lines. They're essentially lines of magnetic force. The term for this is flux. Right? It's represented by the Greek symbol phi. Right? So here's phi. In terms of these, they essentially go from one pole to the other. They're always represented as coming out of the North Pole and going to the South Pole. And they don't have to be straight. They can curve, etc., but they can never cross. Right? Essentially, these lines push each other apart, and so while they may flow parallel to each other, essentially alongside each other, they'll never cross. And I shouldn't really describe them as flow. Nothing really necessarily moves. It's that magnetic force that's actually being shown in there. Right? In terms of our basic law of magnetism, it's pretty much the same as our law of charges, and that is that unlike poles, just like unlike charges attract, and like poles repel. So if you have plus and minus, or north and south, they're going to attract each other. If you have minus and minus, they're going to repel each other. Plus and plus, or south and south, north and north, they're going to repel each other. Right, so here we see these lines of flux essentially coming out of the north side, flowing to the south side. Right, and you can see they're parallel, and you can see they don't cross. On the other hand, if you have north and north, there's no way that they can flow. In fact, they will flow around and back to the southern pole in this situation, but because they can't flow from pole to pole, they're going to repel. So these two magnets would be pushed apart. Same thing would happen if this was south and south. Right? So if we take a look, just opposite poles or unlike poles are attracted to each other. Like poles are going to repel each other and push each other apart. Pretty similar to the way our charges worked, if you think of that. Now, in terms of electromagnets, these are a lot more interesting because we have a lot more control over them. And the way we control them is by using an electric current. Right? Essentially, anytime current throws through a conductor, a wire or any other form of conductor, it generates a magnetic field around it. It's a relatively weak magnetic field, but depending on the amount of charge involved and the size of the wire, etc., you can actually develop a pretty high magnetic field. And if you reinforce it with multiple wires, you can make a pretty strong magnetic field. Right, so biggest issue is current flow in terms of the overall strength. And keep in mind, one of the nice things about electromagnetics is it really only lasts as long as there's current. Right? If you shut off the current, the material will be no longer magnetic. Although in some cases there's a certain residual amount of magnetism, which we'll talk about in a little bit. Right? If you take a look at a wire or a conductor, right? If you see here, this dot shows the current flowing out. Right? So if the current's flowing out, you will have the magnetic field looping around it clockwise. Right? On the other hand, if you have the current flowing in, this plus side represents current flowing in, you still will have a circular magnetic field, but now it will be counterclockwise. Right? If you take two wires and you put them together, if they're in opposite directions, you'll notice the magnetic lines of flux here. These flux lines won't cross. On the other hand, if you're flowing in the same direction, it will reinforce these, right? And it'll flow all the way around it. Now, if you take our wire and you're to look at it on the side, you can see the same setup. Right? In fact, this is governed by what's referred to as the left-hand rule. If you were to grab the wire with your thumb pointing in the direction of current flow and wrap your hands around it, you can see that that magnetic field follows your fingers. Now, if you take multiple wires, right, and if you take them and you make multiple loops, right, this is showing multiple loops or multiple coils here, each of these magnetic fields are going to reinforce each other, right, essentially currents flowing in the same direction, and you can make a much stronger magnetic field. Right? And that's how most electromagnets work. They use a coil of wire to increase the strength of the field. Now, biggest issue, of course, is current flow, right? More current flow, the stronger the field, but there are other issues. One thing is the number of turns of the wire, right? Every time you put a turn or a loop of the wire, you're going to increase the strength of the magnetic field. And of course, as I said, the current flow, right? So it turns out that we use a phrase called ampere turns or amp turns, and these are the number of turns multiplied by the current flow, right? So essentially, if you double the current, you're going to double the magnetic strength. If you double the number of turns, you're going to double the magnetic strength. So those two things are directly linear in terms of the strength of the magnetic field. The other variable you can change is the core material. Essentially, what is that coil wrapped around, right? Doesn't necessarily have to be wrapped around anything. You can use, for example, an air core magnet. An air core magnet is essentially something in the center that has no magnetic material at all. You could use wood. You could also just use an empty cardboard tube, which is filled with air. It will develop a magnetic field. On the other hand, if you use a magnetic core material, something like iron, steel, or one of those other ferro materials, you can dramatically increase the strength of the magnetic field. So that's the other variable you can play around with. And there's reasons why you want to have different core materials. So we will see both air core magnets and iron core magnets, depending on what we want the magnet to do. So the strength of this magnetic field is governed by a property known as the permeability of the material. So a material's permeability will tell you how strong magnetic field that's going to be generated. So for example, if you take a look here on the side, you can see if you use no material, just a straight air core, you're going to get potentially 100 flux lines. On the other hand, if you were to put a iron core with a much higher permeability, you're going to generate up to 1,000 flux lines. It doesn't necessarily 10 to 1. This is just an example to give you an idea of the comparison, but you can dramatically increase the amount of the strength of the magnetic field by using a more permeable material. Other terms used to describe the core material include reluctance, saturation, and residual magnetism. Reluctance is essentially the opposite of permeability. Reluctance is the resistance to magnetism. And the fact is, materials that have a low permeability have a high reluctance. Saturation is essentially means that we have taking the material up to the highest strength we can in terms of its magnetic strength, and all the molecules within there are completely lined up. Right? So as you increase the strength of the magnetic field, more and more of the molecules are going to line up. Once it gets to a certain level where all of them are lined up, then the core material has reached saturation. As I mentioned, some materials will remain magnetized after the current is removed. For example, iron can have a significant amount of residual magnetism. And what you essentially means that once we have lined up all those atoms, when we take the current away, they stay lined up. Right? So that means that the material remains magnetic. We can easily do this in iron, and for at least a brief amount of time, you'll have a permanent magnet, but it will eventually give out and go back to that random orientation, and the magnetism will eventually go away. So just like other technical fields, we need to find a way of quantifying and measuring magnetism and magnetic fields in general. Turns out that magnetism is something that was discovered relatively early in human scientific exploration. It's readily observable, and as a result, a number of different scientists were studying it, and as a result, we have multiple measurement systems. Turns out we actually have three, one based on the English or imperial system, and two based on essentially the metric system. In terms of the English system, we use quantities like flux density, magnetomotive force, etc. The book gets into some details and defines these. We also have a CGS system. CGS stands for centimeter gram second. These quantities like the Maxwell, Gauss, Gilbert. We have a unit magnetic pole, dynes used for force. Again, some details of this you can find in your textbook. But the easiest one and simplest one to follow is the MKS system because it uses meters, kilograms, and seconds. So it defines it in the same system as other quantities across the SI system. So we have the Newton, for example, for force. We have the Weber, something you're probably not familiar with, for magnetism. But again, go in the book, it has a lot of details on this. One thing you definitely should understand how to figure out is magnetic polarity. Anytime you're dealing with an electromagnet, it's going to involve a series of coils being wrapped around some core. And the standard rule for this is what's referred to as the left-hand rule. So if you were to grab the core material or grab around the windings with your left hand, right? Your fingers are essentially the direction of the windings, right? Because you can see them here. They're going in the directions that the windings are going, right? And of course, that's the direction the current is flowing in the windings. And then your thumb points in the direction of the polarity, so it points towards the north pole of the magnet, right? So if you were to reverse charge, right, your hand would have to be flipped around and it would actually reverse the direction of the magnet. So one of the interesting things about magnets, you can easily reverse them. Now, it turns out that magnets are used in a whole variety of electrical equipment. We have essentially just electromagnets that are used for various devices. We use them in measuring instruments. We're going to talk about inductors a little bit later. Transformers and motors all use magnetic devices. It's one of the ways electricity is used to generate motion. Another common device that we're all familiar with is as a speaker, right? The audio speakers on all different pieces of equipment use magnetic devices, and they're kind of interesting because they use multiple cores in the process. So the way a speaker works is it uses both a permanent magnet and an electromagnet. Electromagnet is wrapped around an air core, right? And in front of that air core is this cone. All right, so we take a look here. So the way this works is the base of the cone has a diaphragm, and the diaphragm is held in place by the permanent magnet. So the diaphragm does not move around until we send charge through this. If we send charge in one direction, that's going to overcome the permanent magnet. It's going to force the cone to flex out, generating certain frequencies of noise. On the other hand, if we send charge in the other direction, it's going to flex the diaphragm in, opposing the permanent magnet, and it's going to then generate different frequencies. So the permanent magnet is used to hold the whole system in stable, and then the electromagnet is used to flex this cone, the diaphragm, the base of this cone, in and out. The faster it does it, the different frequencies of sounds we're going to get, the higher and lower volumes we're going to get. So to summarize our information on electromagnets, it turns out that different materials have different levels in terms of the strength of the magnets they can be manufactured into. Essentially, we have three different categories. Ferromagnetic means a material that can be magnetized relatively easily. Paramagnetic is a material that's more challenging to magnetize, but it's possible. And diamagnetic means a material that cannot be magnetized, right? Iron, for example, is a ferromagnetic material. Copper, for example, is a diamagnetic material. Anytime current flows through a conductor, a wire, etc., it's going to generate a magnetic field around the outside of it. And in terms of the direction and how the coils are run, it's going to determine the magnetic polarity. And of course, you can use the left-hand rule, not the right-hand rule, the left-hand rule to determine the polarity, where again, you wrap your fingers in the direction of the current flow and your thumb points towards the North Pole. In terms of the strength of the electromagnetic you're going to create, it's going to be determined by the number of turns and the amount of current or amps. These combined together are known as amp turns or ampere turns. The stronger the material, the better its permeability is, the stronger the magnet you're going to be able to increase. Iron, for example, has a very high permeability. Things like air, wood, etc. have very low permeabilities. As a result, they're not going to generate a very strong magnet. There are multiple systems used to measure and quantify magnetism. We have our English system. We have both a CGS and an SI system. You should be familiar with the various quantities associated with those. Keep in mind, objects don't necessarily stay magnetized. They can be demagnetized. For example, if you run through an AC magnetic field, that will eliminate it. Remember, AC is going to flip things back and forth, so that's going to eliminate the magnetism. You can also damage a magnet by hitting it very hard. That can cause the atoms to get rearranged inside, or heating it. Again, heating material tends to make atomic movement that much faster, so they get rearranged and become more random if they're heated.